Okay, now let's talk about blood pressure regulation. And I want you to have your blood pressure equation ready to go. Remember, blood pressure equals cardiac output times peripheral resistance. And make sure that you've written it out the long way. So blood pressure equals heart rate times stroke volume times the 8 times the length times the viscosity over the radius to the fourth times pi, I guess. Okay, and as we go through the blood pressure regulation, you should look at that equation and make sure that it makes sense. So blood pressure regulation through the sympathetic nervous system. Okay, how do we do that? Let's start here where it says start here. We have some blood loss. Okay, so we have just reduced our volume, which now reduces our pressure, right? Because we have a closed system. Usually now it's open and we've just lost a lot of blood. So your body senses that. You don't have to remember this, but you have a couple of sensors. One is in your carotid artery, one is in your aorta. And when they sense a decrease in strength or a decrease in blood pressure, then they send signals to the brain, which then sends signals in the brainstem, then sends signals directly to the heart, directly to the heart muscles, directly to the electricity system in the heart, directly to the muscles surrounding the vasculature. So in the vasculature, it creates vasoconstriction. And remember, vasoconstriction means that we just decrease that radius, which increases our resistance by a lot, which increases our blood pressure. But the other ways that it works is that it increases the heart rate by working directly with the electrical system in the heart, speeds up the pace. So remember, cardiac output is heart rate times stroke volume. And since we increase the heart rate, that increases the cardiac output, which increases the blood pressure. But then we also work directly on the muscle fibers. And this is where that contractility comes in, right? It stretches it like a rubber band. And so it can eject more. And that is working directly on the stroke volume. So we increase the stroke volume, which increases the cardiac output, which increases the blood pressure. If it doesn't make sense, maybe go through it one more time. So the other way that we regulate our blood pressure is through the renin-angiotensin-aldosterone axis. Okay, so there's some overlap with the sympathetic nervous system and this one, but we are going to talk about them as if there isn't. But of course, you know, we can't be complete reductionists. Like the body doesn't work like that. It's super complex. And so just know that this actually works with the sympathetic nervous system. So whether it's because of the sympathetic nervous system or whether it's because we just lost a whole lot of blood volume, the kidneys also sense that it's not getting as much flow. And the function of your kidneys is basically to filter out your blood. And so whenever it doesn't get as much in, then it activates the system. So it activates renin, which acts in a couple of different ways. For this particular system, I'm okay if you don't have it completely memorized. But basically, a decrease in blood flow results in kidneys secreting renin, which triggers this chemical cascade that basically results in more vasoconstriction. And remember how vasoconstriction affects our blood pressure by decreasing the radius, which increases the resistance, which increases the blood pressure, right? And so vasoconstriction and by salt and fluid retention. And so remember, if you retain salt, you're going to retain fluid, which will then increase your blood volume, which will then increase your stroke volume, which will then increase your cardiac output, which will then increase your blood pressure. And so You don't have to memorize the angiotensin and aldosterone because it's a little bit more complex. But do know that basically the decrease in blood flow activates the system and then further vasoconstricts your arteries and arterioles, and then increases salt and fluid retention. Okay. And you should know how that works within that algebraic equation of blood pressure. So let's go through this case. A man with severe hypertension, so severe high blood pressure, was recently diagnosed with a pheochromocytoma, which is a tumor that secretes epinephrine and norepinephrine. And so remember, these are the hormones and neurotransmitters if we're working in the nervous system, but hormones that are secreted whenever your sympathetic nervous system is activated, right? So basically, he has a tumor that mimics his sympathetic nervous system, that fight or flight response. So describe why his blood pressure is elevated. Press pause, take a few minutes, look at the equation and see if you can figure out all of the different factors that are being affected and how they contribute to an increase in blood pressure. And once you think you've got it, go ahead and press play. So let's go through it. Remember, the sympathetic nervous system, or epinephrine or norepinephrine, sends a signal to your heart, to the electrical system in your heart, to increase your heart rate. So that's going to increase your heart rate, increase your cardiac output, increase your blood pressure. It's going to send a signal directly to the muscle fibers, which are going to increase contractility. That's going to stretch out those fibers like a rubber band and squeeze them, right? So that's going to increase your stroke volume, which will increase your cardiac output, which will increase your blood pressure. It's also going to not do this, but it's going to cause the muscles around your arterioles to constrict, which will decrease the resistance, which will increase or decrease the radius, which will increase the resistance by a lot, which will increase the blood pressure. But the other way, if we look at the renin-angiotensin-aldosterone axis, is that it also activates that system, which results in further vasoconstriction. So further decrease in radius, further increase in resistance, further increase in blood pressure. It also results in more salt and fluid retention, which is going to increase your stroke volume and increase your cardiac output and increase your blood pressure. So why are these things working on the same mechanisms, on the same factors? Well, because anything in your body that is really important is also really redundant. If you're bleeding out, you really do need to maintain your blood pressure to be able to oxygenate your brain, right? To be able to continue to oxygenate your heart muscle and your kidneys. You could probably do without your toes, but the brain and the heart and the kidneys and all of these things are really important. So if you're losing blood and it was because, of a particular mechanism, you need backup. And so all of this stuff works on the same factors because it is redundant, and that means it's very important. When we talk about sexual health lecture, we'll talk about the redundancy of erections, because that's really important for like reproduction, right? And so blood pressure and erections, male and female, very important to our survival. And so at this point, if you don't understand what we just went through, go ahead and do it again, or message me on Slack to see if we could just go over it in a different way.